Good afternoon, calculus today. So I just want to talk about chapter 7, starting with chapter 7, 7.1. So chapter 7 is all about the bunch of different techniques of integrations. So it's just getting more in depth with calculus, especially for calculus BC. Okay, so we'll take a look at that integration, all those techniques. So due to the fundamental theorem of calculus, so we can integrate a function. We know that the antiderivative. So this is the indefinite integral. So those are the formula that we talked about previously for chapter 5. Power rule, integrals of 1 over x, which is ln of absolute value of x plus constant c. Again, this one is all the indefinite integral with the constant c at the end after you integrate it. Integrals of e to the power of x dx, e to the power of x plus c, and then integrals of a to the power of x, which is a to the power of x over natural log of a plus constant c. And the trigonometric integrand, so those are the formula that you guys already recognize. Sinh and cosh, we barely talk about that. Sometimes we have to use it, especially for people who want to major in civil engineering. Okay, so or any kind of for architect engineering. So those are the one that you guys need to apply. So integrals with the inverses, like the pattern of 1 over x squared plus a squared. So it's 1 over a, inverse of tangent of x over a plus constant c. So those are the one that we have on the formula quiz already. And also the one along with 1 over square root of a squared minus x squared. So which is the inverse of sine of x over a plus constant c. So for this chapter, we have to use some of the integration formula as well. Okay, so the substitution rule we talked about in 5.5 already. And the other general technique, okay, so that's what we'll talk about, integration by part. So that's what we want to start at first. Okay, so 7.1. So let me show you the way to come up with the integration by part formula. Okay, so back to the product rule. So we do have d over dx, f of x times g of x, which is f of x, g prime of x plus g of x times f prime of x. And then if we try to integrate it on both sides, so we get back to f of x, g of x. But the thing is that if we try to solve for one term into another, so let's say that we separate the integral. So we do have two parts of the integral here. So f of x, g prime of x. We can always separate them. So once you separate it, and we try to solve for the first half of the integrand, so we got f of x, gx, g of x, minus the integrals of g of x times f prime of x dx. Okay, so then that would be considered an integration by part formula. Okay, so using it. So let's say that we do have two functions. One is u equals f of x, v equals g of x. So du can be founded by f prime of x dx, because now we want to take the derivative implicitly. And then dv, which is v prime, is g of x, g prime of x times dx. Again, taking the differentials, the derivative implicitly. And then using the formula with the substitution rule, so we end up with integrals of u dv equals uv minus integrals of v du, which is the similar pattern as what you can see that from the previous one, which is f prime of x. F of x, g prime of x dx is the same as f of x, g of x minus integrals of g of x, f prime of x dx. So this one, those two formula, they're pretty much the same thing. But instead of using f of x, g of x, we're using u and v. And u prime, v prime. Okay, so this one, here's one of the examples. So suppose that we choose f of x, x, and then g prime of x is sine of x. The reason why that we choose f of x, x, because that we want to reduce down the power to the lowest term once we take the derivative. So we got f prime of x equals 1, and g of x, once you integrate it, we do have negative cosine of x. So using the formula, integration by part. So we do have integrals of x sine of x dx. It's f of x, g of x, which is x times negative cosine of x. And then the integrals of g of x, f prime of x, which is integrals of negative cosine of x dx. Negative, negative, so it turns out to be positive. So the first part of the integral here, so this one is done already, so there's no need to integrate the first half. And then for the second half, this one, once we integrate it, we do have sine of x. So eventually, for the integrals of x sine x dx, is negative x cosine of x plus sine x plus c. Okay, so here's another way that I can come up with this using u and dv. So pretty much the same kind of idea. Okay, so showing the similar structure here, but we just changed that to variable u and dv. Okay, so now let's try another example here. So for cosine of x, well, we started with this one, x sine x dx, and express that in terms of the simpler integral, cosine of x. So this one will give you like a more complicated structure if you try to do it the other way around. So just want to showing you that. So make sure that you need to choose the right u for this. So if you cannot reduce down the power, so you probably don't want to use that as u. Okay, so this one is what this slide is showing. Okay, so now let's try another one. So we don't know what integrals of natural log of x is, so we use that u as natural log of x, because we do know the derivative. Derivative of that would be 1 over x. And dv is just the same as dx. Once you integrate that dv, so we do have v equals x. So because you want to take the integral on both sides. And then using that integration by part formula, so integrals of natural log of x dx, so which is uv minus integrals of v du. So we do have integrals of x dx over x. You see that x's right here, so it's got cross cancel out. So we just need to integrate that integrals of dx, which is x. And don't forget to add the constant c, because this one is the indefinite integral. Okay, so now let's just try another one. So integrals of t squared times e to the power of t dt. So choosing that u is t squared. Again, we want to reduce down the power once we take the differential. So that's what we got here. And then dv is just e to the power of t dt, integrals of e to the power of t, which is the same thing. So using the integration by part formula, we do have t squared e to the power of t minus 2 times the 2. We just want to pull that out because that's just a coefficient. Integrals of t e to the power of t. And for those who might be wondering, well, what about over here? Looks like we cannot integrate it. That's right. So that means we're going to be using integrated by part once again. So using that integration by part, we choose that u equals t, and then dv equals e to the power of t dt. Okay, expand the whole thing. So we do have the integrals. So t e to the power of t. And then once we integrate it, so we do have t e to the power of t minus integrals of e to the power of t. This one's supposed to be equal sign here. Sorry about that. The one that I'm just pointing at right here. So this one's supposed to be the equal sign. So this one equal to t e to the power of t minus e to the power of t plus c. And then we just plug in back to the previous setup here. And then basically just multiplied it out. So c just like c times negative 2. c1 is just negative 2 times c1. Okay. So got to be careful which one that you choose for e to the power of x or sine of x. Okay. So this one, here's another example. So try to using that integrated by part. Okay, so using u equals e to the power of x, dv equals sine of x. So basically you end up with something similar. It doesn't matter which part that you set up as u dv for this, because for both of them you cannot reduce down the power no matter what you're doing. But we can use that repetition. As you can see that the left hand side here, which is the same as this part right here. So we just want to group the like terms together. So take that integrals of e to the power of x sine x dx to the left hand side, so we can combine them. So we got 2 integrals of e to the power of x sine x, and then basically we just solve for the integral, so simply divide it by 2. And don't forget to add the constant c at the end. So this figure illustrates the example showing the graph e to the power of x sine x. So once you take the integral, you get the capital F of x. So they're quite similar. So we combine the formula for the integration by part with part 2 of FTC, part 2. So we can evaluate definite integral by part. So using that, we can use the definite integral. So like this one here, integrals from 0 to 1, inverse of tangent of x dx. So u would be inverse of tangent of x. dv just dx. Derivative of u, which is dx over 1 plus x squared. So v is x. And using integration by part formula, so we do have uv minus integrals of u dv, or v du. So here's what we got. So using part 2 of FTC, plug in the number f of b minus f of a for the first half. And then the second half after you integrate it. And then we're using part 2 of FTC as well. So for the first half, we got pi over 4. So now the second half. So what's the integrals of x over 1 plus x squared? So using that, the u substitution formula, so we set t equals 1 plus x squared. So dt would be 2x. So x dx equals 1 half dt. So by plugging all that setup here, so 1 half integrals from 1 to 2 dt over t. And also we just changed the t value. So when x equals 0, we got t equals 1, like what we did for 5.3. And then when x equals 1, so t equals 2, this setup. And then integrate it using that part 2 of FTC, so we end up with 1 half natural log of 2. And then by plugging back to the previous equation here, so pi over 4 minus natural log of 2 over 2. And that's the integrals of inverse of tangent of x from 0 to 1. So inverse of tangent of x, it's greater than, for x is greater than 0, greater than or equal to 0. So the integral in the example can be interpreted as the area of the region shown here. Okay, so once you find the area from 0 to 1. So here's another example. So integrals of sine n to the n power and then dx. So it's negative 1 over n cosine of x sine of x to the power of n minus 1. And then plus n minus 1 over n. Well, this one is just the formula that we have. So this is called the reduction formula because the exponent n has been reduced down to n minus 1 and n minus 2. Or we can use that integration by part formula. So set up u equals inverse of sine of n minus 1 x. So du would be n minus 1 sine of n minus 2 power x cosine of x, the chain rule dx. And dv just sine of x dx. So v is negative cosine of x for the integral of sine of x. So putting it back to the integration by part formula, so we do end up with this, the pattern. So this one is just the structure showing the proof. Proving the formula, making sure that it's always true. Since cosine square of x is 1 minus sine square of x, so we do have the replacement. Okay, so negative cosine of x times sine of power n minus 1 of x plus n minus 1 times the integrals of sine of x to the power of n minus 2 dx. And then minus n minus 1 integrals of sine of x to the power of n dx. Again, this one is just a substitution. So we end up with this. Again, this one is just the optional proof that you need to know. Okay, so showing the pattern. So now, it's easier to using the reduction formula. What happens sometimes you forget about it, we can always do the proof. Okay. So one thing that you may notice, integrals of sine of x dx, if n is odd, so we can express that the sine of x to the power of n if n is odd, so that's the same as the integrals of sine of x. So what about integrals of sine of x to the power of 0 dx? It's the same as integrals of dx. So if n is even, so that means it's just integrals of dx. Okay, so that's it. So for the last two slides, they're just like the proof for any kind of complicated structure for the formula. So those are the optional stuff that you need to know. So thank you for watching the video today. So I'll see you guys next time.